Hello everyone, I hope you're doing well. Today I'm going to continue my classical mechanics playlist by talking about, bumped the paper, velocity and acceleration. Okay, so I want to introduce this idea of a scalar. Now this word might be unfamiliar to you, but I promise you the concept of a scalar is extremely familiar to you. It's quite simply anything with a magnitude. Okay? Now, you might be kind of confused at first as to what this is, but we can just think of a regular number, right? So, here's an example. 2, 3, 56, doesn't matter. Because 2 does not have a direction, 3 does not have a direction. That would make 2 and 3 vectors. It's just a magnitude of 2, size of 2. That's it. Okay, so now that we have that out of the way, I want to talk about velocity, acceleration, and I'll also talk about speed too. So, first I want to talk about speed versus velocity. Okay? So, speed, notice the S there, is a scalar. And it's measured in units of meters per second. Okay? So it's how many meters we travel in a given second. Now velocity, once again notice the V, is a vector. So you can remember put V to V, S to S. And it's going to have the same units of the meters per second, but it's also going to have a direction. And we can draw it as a vector, those little helpful arrows. So now I want to talk about a formula to calculate the average velocity of something. So our average velocity, which we can represent with this little bar, okay? Is equal to the displacement over the change in time. Delta x over delta t. Delta always means change in, just as a reminder. And here we are just going to deal with this in one dimension. We'll talk about 3 dimensions, 2 dimensions, whatever, however many dimensions you want in a moment. But for now, I'm just going to focus on the x direction, one dimension. So we can say that, well, our change in x is equal to x at some time t plus the change in time minus that initial position x at time t. Okay? And we're just going to make sure we divide that by delta t. Okay, so that's average. Now I want to talk about instantaneous. If you're not familiar with calculus, this might seem a little bit confusing to you at first. I hope you can still grasp it conceptually though, but you might not be able to do the calculations that would go with this, like the problems, for example. So what I recommend you do is you brush up on your calculus. There isn't really an easy way to, cheat it. You just kind of have to know it. Okay? Well, if we want to calculate instantaneous velocity, so this is the velocity at a given moment in time. For example, if I roll my pencil and I want to know what it is exactly 0.1 seconds after I roll it, we will end up using this formula. So what we're going to do is we're going to do something called taking a limit. And we're going to take this limit as our change in time, delta t, is approaching 0. Really what this means is that as we make our delta t here smaller and smaller and smaller, we want to find the value that velocity approaches. Okay? Obviously, you can't actually divide by 0, so we can't just plug in 0 for things. But we're going to find the value as it approaches 0. Okay? So what we can find is that the x of time plus the change in time is going to get very, 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 very small. That change in time will get extremely small, and that this will nearly be equal to the x at some time t. Now I'm just going to divide everything by delta t, which will be near 0 as well. And what we're going to find is that if you know calculus, this is the exact definition of a derivative. Here, dx is some very, very, very small change in our position x, and dt is some very, 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 very small change in time. So derivatives, which is what this is the derivative of position with respect to time, are evaluated at a very, very, very tiny scale, which I will call the 1 over infinity scale. And at this scale, we're going to see something similar to this. So the x-axis will be any horizontal line here. So if this vector right here is our position vector at time t, okay, we can say that if we let some very small time pass, we're adding a very, very small amount of x to this, dx. And this is not drawn to scale, by the way. And then this taken as a whole, those two vectors added, taken as a whole, will just be this vector, which is x of t plus our very, very small delta t. Okay, so we're just adding a very, very small amount. Technically, this is an approximation, but it's at the 1 over infinity scale, which, quite frankly, is not an approximation on a very large scale. It really does not matter, in case you're uncomfortable with making an approximation like that. Now, I want to move on from this, and we are going to do the exact same thing. Okay, I want to talk about acceleration. Well, the average acceleration is going to be equal to the change in velocity over the change in time, which we can write in the same way. We're going to write that in the same way as we did position. And then, I think you can see where this is going. The instantaneous acceleration is equal to the limit, as our change in time approaches 0, of the velocity at t plus delta t, which is going to 0, minus the velocity at time t, all over this very, very small change in time. And we can also write this as a derivative, the derivative of velocity with respect to time. Okay? So, really fast, I just kind of want to sum everything up so far. So if we have a position vector, a velocity vector, and an acceleration vector, we can find that by taking the derivative with respect to time, d dt, of position, we get velocity. If we take this derivative with respect to time of velocity, we get acceleration. And really fast, I want to note that the units of acceleration are meters per second, which we can just say is meters per second, meters over seconds times seconds, which is just meters per second squared. Okay? So I should have said that earlier, but that is our unit for velocity. or acceleration. That's our unit for acceleration. Now, if we want to go straight from position to acceleration, we can take the second derivative of position, x, with respect to time, and we'll write it as that. Okay, so then we can also say that acceleration a equals d2x over dt squared, which is the second derivative of our position with respect to time. Okay, now that my page is flipped, I'm going to talk about three-dimensional velocity and acceleration. Okay, so here we have that velocity equals dr over dt, the derivative of our three-dimensional position vector, which is r, with respect to time. Okay? And acceleration is going to stay exactly the same as the derivative of velocity with respect to time. We could write this as the second derivative of position with respect to time, d2r over dt squared. Okay? And now I want to talk about a good notation for this, because it can start to get cumbersome if every time we want to write velocity or something, we write it as this. So what we can do to still show that it is a derivative of position is we can use Newton's notation, which was just to put a dot over the letter that we're using to represent this, the variable r, for every time derivative of r there is. So the acceleration, which is the second derivative of the position vector r with respect to time, gets 2 dots. Velocity is only the first derivative, so it gets 1. Okay? And now, just to end things off, I want to show that the first time derivative of r is the same thing as the time derivative of the magnitude of its component, x, in the x hat direction, plus the first time derivative of y in the y hat direction, plus the first time derivative of z in the z hat direction. If you're not comfortable with this notation yet, just write it out using this. Just replace the r's with an x, y, and z when you go to write that there. Now, it's important to note that you might have to do a product rule between these two if the unit vector is not constant. But in our case, x hat, y hat, and z hat are all equal to 0, which is a constant, and the derivative of any constant is 0. Now, I'm actually going to write that as the time derivative, even though what I wrote there was true too. I'm going to try to keep it in physics instead of math. So, now, and if you don't quite understand all derivative rules yet, you can think about this one pretty easily, because the rate of change, which is the derivative of any constant, is 0, because the constant doesn't change. It stays the exact same. So it's just going to be 0. 0 rate of change. Okay? And we can say that because these unit vectors are constant, it's 0. So if you went through and did the product rule for this, you would end up with this exact same thing as just doing the derivative of that, plus that, making the unit vector direction. Now, what's very important is that when we get out of Cartesian coordinates, unit vectors can start to change with time, and we will have to account for that. All right? Well, I think that's going to about do it for this video. Hit the like button, subscribe if you want. But, make sure to have a good day, the best day you can have. Good night, good day, whatever works for you. All right. See you in the next video, I hope.